Hello again. Today we are going to talk about series resistive inductive circuits, RL circuit. Up until this point in other videos, we've covered inductance, we've covered capacitance, inductive reactance, and capacitive reactance. Today we're actually going to work on circuits that exist in real life, a resistive inductive circuit. And what we see here are what seem to be three triangles. These aren't actually triangles. I know it's a trick. They're actually vectors that are showing us the phase relationships between resistance, inductive reactance, and then our overall impedance, which of course we know is defined as the total opposition to current flow. We also see on display here in our voltage triangle, the voltage through the resistor being in phase, of course, with the current through the resistor, because frequency doesn't affect resistors. A 10 ohm resistor in DC and a 10 ohm resistor in AC are treated the same way. They use 100% of the power, so there's no wasted energy there. So the voltage and the current are in phase. What we also see in phase is the total current and the current through the inductor. Reason being is because we're in a series circuit. And as we know from DC theory, in a series circuit, current is always the same. So current is going to be in phase no matter what in a series circuit. Then we see at the 90-degree angle, the voltage applied to our coil, our inductor. And this vector right here represents our little acronym known as ELI. ELI is how we understand what happens to voltage and current in an inductor. Voltage is going to lead current by 90 degrees through an inductor. And that's what we see on display in these vectors that we have arranged into triangles. So now let's do some actual work with it, right? We have a 40 ohm resistor here and a 53.1 millihenry inductor. And as we know, for electrical calculations, millihenries aren't going to help us. So we need to convert that into X of L using our 2 pi FL, 2 pi for life formula. We have the 60 hertz of frequency here, and we have our henries, what we measure inductors in. We perform our calculation, and we come up with 20 ohms for the ohmic value of that inductor. So now we can start to put together our impedance triangle. And the impedance triangle is only ever going to show up in series. If we take what we know, the laws of series and parallel circuits, we know as we add resistors in series, total resistance goes up because we add those resistors. In parallel, the more resistors we add, total resistance goes down. So we will only see the impedance triangle in series. So now, because everything through a resistor is in phase, phase is always at the 0 point on our graph, the horizontal, the x-axis, or the adjacent side of our right triangle here. And we have 20 ohms of inductive reactance. Of course, we can't just add them up like we did resistors, because inductors are going to take voltage and current out of phase with each other. So we can't add them up straight like resistance. They're 90 degrees out of phase with one another. So we're going to use Pythagorean's theorem, which will mean that impedance will equal the square root of the resistance squared plus the x of L, the inductive reactance squared. In this case, 40 squared plus 20 squared, which gets us an impedance of 44.72 ohms. So now we have our E total, 120 volts, and we have our Z. You will never see a total subscript with Z because, again, impedance means the total opposition to current flow. And that's our 44.72 ohms. Now we can solve for total current here. Everything's going to see in this series circuit, because we know the laws of series, we end up with 2.68 amps. Excellent. So now we can start putting together our other triangles, because of course we're going to have to know how much voltage is going to be dropped on the resistor, how much voltage is going to be applied to our inductor, how much total voltage do we have. Well, that's the easy one. The horizontal lines, our hypotenuses here, are always going to be our longest lines. They're always going to be our totals. So we already know our total voltage. Our total voltage here is going to be 120 volts. So now, how do we figure out how much voltage is applied to the resistor? Well, we use the laws of series circuits. We know everywhere we're going to have 2.68 amps. And if Ohm's law applies, it always applies, we're going to have voltage is equal to resistance, or ohms, or X of L, or Z, times the current will equal the voltage. Well, we got 40 ohms of resistance here. We multiply that by 2.68, and what do we get? 107.2 volts dropped on our resistor. So we just subtract 120. We subtract 107.2 from 120? Of course not. We're 90 degrees out of phase, and it would violate Ohm's law. So we're going to take 2.68 amps. We know is going to be applied to our inductor here because of the laws of series circuits. And we're going to multiply it by our inductive reactance, 20. And we see that we're going to drop 53.6 volts on our inductor. And again, the beauty of math is we can work formulas forward and backwards. We already knew what the total voltage was. So can we check to see that we're right? Absolutely. We would take E of R squared plus EX of L squared, take its square root, and we would get E total, our hypotenuse here. A squared plus B squared equals C squared. And at this point, the power becomes a lot simpler to solve for. Of course, we could always solve for apparent power, power delivered, supply power. That's always measured in volt amps. Apparent power, all the power, volt amps. We can take the total voltage, 120, multiply that by our total current, 2.68, and we get 321.6 volt amps. That's what this circuit will draw. That's the easy bit. The harder thing to figure out would be, how do I solve for true power, the power that's not wasted, the power that goes through the resistive part of the circuit, where it uses all that power to perform work over time for us, which we call watts. Well, that goes through the resistor. You have your 107.2 volts and your 2.68 amps. We multiply those together, and we get 287.3 watts of true power. Nothing there is wasted. So now we can figure out how much foam we have in our graph here, how much wasted power our volt amps in the reactive part of the circuit are VARs. 53.6 times our 2.68 amps, 143.64 volt amps react. That's our wasted power here. So we know that the circuit in its entirety isn't all foam, and we want to figure out how efficient our circuit is. And that's a measurement called power factor. Power factor will tell us how efficient a circuit is, because we're going to have wasted power. Power factor is true power divided by apparent power, or the cosine function of an adjacent over a hypotenuse, which means we can use any side of the triangle we want, because the angle will always be the same. So I can take my 40 ohms of resistance, divide it by my 44.72 ohms of impedance, adjacent side, hypotenuse, and we find that our power factor is 0.894, or 89.4% efficient. We're wasting a little over 10% of the power applied to this circuit. And the reason why I leave it in decimal form is because I want to know how far out of phase our voltage is with our current, because of our inductor. And that'll be angle theta. And because we use the cosine function to find our power factor, I inverse cosine. Cosine negative 1.894. We do second function cosine 0.894 on our little Texas Instrument scientific calculator, and we discover that we have a 26-degree out of phase condition here. Voltage is leading current by 26 degrees. I hope that you find this video helpful. If there's anything you would like covered, please leave that in the comment section, and thank you for all that you do. Have a wonderful day.